Quantum computing studies theoretical computation systems that make direct use of quantum mechanical phenomena, such as superposition and entanglement, to perform operations on data. Quantum computers are different from digital electronic computers based on transistors, whereas digital computers require data to be encoded into binary digits, each of which is always in one of two definite states. Quantum computation uses quantum bits, which can be in superpositions of states. A quantum Turing machine is a theoretical model of such a computer, and is also known as the universal quantum computer. Quantum computers share theoretical similarities with non-deterministic and probabilistic computers. The field of quantum computing was initiated by the work of Paul Benioff and Yuri Manin in 1980, Richard Feynman in 1982, and David Deutsch in 1985. A quantum computer with spins as quantum bits was also formulated for use as a quantum space-time in 1968. As of 2016, update, the development of actual quantum computers is still in its infancy, but experiments have been carried out in which quantum computational operations were executed on a very small number of quantum bits. Both practical and theoretical research continues, and many national governments and military agencies are funding quantum computing research in an effort to develop quantum computers for civilian, business, trade, and national security purposes, such as cryptanalysis. Large-scale quantum computers would be able to solve certain problems much more quickly than any classical computers that use even the best currently known algorithms, like integer factorization using Shor's algorithm or the simulation of quantum many-body systems. There exist quantum algorithms, such as Simon's algorithm, that run faster than any possible probabilistic classical algorithm. Given sufficient computational resources, in theory a classical computer could be made to simulate any quantum algorithm, as quantum computation does not violate the Church-Turing thesis. Quantum computers, on the other hand, may be able to efficiently solve problems that no classical computer would be able to solve within a reasonable amount of time. Basis. A classical computer has a memory made up of bits, where each bit is represented by either a 1 or a 0. A quantum computer maintains a sequence of qubits. A single qubit can represent a 1, a 0, or any quantum superposition of those two qubit states. A pair of qubits can be in any quantum superposition of 4 states, and 3 qubits in any superposition of 8 states. In general, a quantum computer with qubits can be in an arbitrary superposition of up to different states simultaneously. A quantum computer operates by setting the qubits in a controlled initial state that represents the problem at hand and by manipulating those qubits with a fixed sequence of quantum logic gates. The sequence of gates to be applied is called a quantum algorithm. The calculation ends with a measurement, collapsing the system of qubits into one of the pure states, where each qubit is 0 or 1, decomposing into a classical state. The outcome can therefore be at most classical bits of information. Quantum algorithms are often non-deterministic, in that they provide the correct solution only with a certain known probability. An example of an implementation of qubits of a quantum computer could start with the use of particles with 2 spin states, down and up, but in fact have a system possessing an observable quantity A, which is conserved under time evolution such that A has at least 2 discrete and sufficiently spaced consecutive eigenvalues, is a suitable candidate for implementing a qubit. This is true because any such system can be mapped onto an effective spin 1/2 system. Mechanics. A quantum computer with a given number of qubits is fundamentally different from a classical computer composed of the same number of classical bits. For example, to represent the state of an n-qubit system on a classical computer would require the storage of 2 n complex coefficients. Although this fact may seem to indicate that qubits can hold exponentially more information than their classical counterparts, Care must be taken not to overlook the fact that the qubits are only in a probabilistic superposition of all of their states. This means that when the final state of the qubits is measured, they will only be found in one of the possible configurations they were in before measurement. Moreover, it is incorrect to think of the qubits as only being in one particular state before measurement, since the fact that they were in a superposition of states before the measurement was made directly affects the possible outcomes of the computation. For example, consider first a classical computer that operates on a 3-bit register. The state of the computer at any time is a probability distribution over the different 3-bit strings 000, 001, 010, 011, 100, 101, 110, 111. If it is a deterministic computer, then it is in exactly one of these states with probability 1. However, if it is a probabilistic computer, then there is a possibility of it being in any one of a number of different states. We can describe this probabilistic state by 8 non-negative numbers A, B, C, D, E, F, G, H. There is a restriction that these probabilities sum to 1. The state of a 3-qubit quantum computer is similarly described by an 8-dimensional vector, called a ket. Here, however, the coefficients can have complex values, and it is the sum of the squares of the coefficients' magnitudes that must equal 1. These squared magnitudes represent the probability of each of the given states. However, because a complex number encodes not just a magnitude but also a direction in the complex plane, the phrase difference between any two coefficients represents a meaningful parameter. This is a fundamental difference between quantum computing and probabilistic classical computing. If you measure the 3 qubits, you will observe a 3-bit string. The probability of measuring a given string is the squared magnitude of that string's coefficient. Thus, measuring a quantum state described by complex coefficients gives the classical probability distribution, and we say that the quantum state collapses to a classical state as a result of making the measurement. Note that an 8-dimensional vector can be specified in many different ways depending on what basis is chosen for the space. The basis of bit strings is known as the computational basis. Other possible bases are unit length, orthogonal vectors, and the eigenvectors of the Pauli X operator. Ket notation is often used to make the choice of basis explicit. For example, the state in the computational basis can be written as where, e.g., the computational basis for a single qubit is an. Using the eigenvectors of the Pauli X operator, a single qubit is an operation. While a classical 3-bit state and a quantum 3-qubit state are both 8-dimensional vectors, they are manipulated quite differently for classical or quantum computation. For computing in either case, the system must be initialized, for example into the all zeros string, corresponding to the vector. In classical randomized computation, the system evolves according to the application of stochastic matrices, which preserve that the probabilities add up to 1. In quantum computation, on the other hand, allowed operations are unitary matrices, which are effectively rotations. Consequently, since rotations can be undone by rotating backward, quantum computations are reversible. Finally, upon termination of the algorithm, the result needs to be read off. In the case of a classical computer, we sample from the probability distribution on the 3-bit register to obtain one definite 3-bit string, say 000. Quantum mechanically, we measure the 3-qubit state, which is equivalent to collapsing the quantum state down to a classical distribution, followed by sampling from that distribution. Note that this destroys the original quantum state. Many algorithms will only give the correct answer with a certain probability. However, by repeatedly initializing, running and measuring the quantum computer's results, the probability of getting the correct answer can be increased. In contrast, counterfactual quantum computation allows the correct answer to be inferred when the quantum computer is not actually running in a technical sense. though earlier initialization and frequent measurements are part of the counterfactual computation protocol. For more details on the sequences of operations used for various quantum algorithms, see Universal Quantum Computer, Shor's algorithm, Grover's algorithm, Deutsch-Jojar algorithm, amplitude amplification, quantum Fourier transform, quantum gate, quantum adiabatic algorithm and quantum error correction. Potential integer factorization, which underpins the security of public key cryptographic systems, is believed to be computationally infeasible with an ordinary computer for large integers if they are the product of few prime numbers. By comparison, a quantum computer could efficiently solve this problem using Shor's algorithm to find its factors. This ability would allow a quantum computer to decrypt many of the cryptographic systems in use today, in the sense that there would be a polynomial time algorithm for solving the problem. In particular, most of the popular public key ciphers are based on the difficulty of factoring integers or the discrete logarithm problem, both of which can be solved by Shor's algorithm. In particular, the RSA, Diffie-Hellman, and elliptic curve Diffie-Hellman algorithms could be broken. These are used to protect secure web pages, encrypted email, and many other types of data. Breaking these would have significant ramifications for electronic privacy and security. However, other cryptographic algorithms do not appear to be broken by those algorithms. Some public key algorithms are based on problems other than the integer factorization and discrete logarithm problems to which Shor's algorithm applies, like the Michaelis cryptosystem based on a problem in coding theory. Lattice-based cryptosystems are also not known to be broken by quantum computers, and finding a polynomial time algorithm for solving the dihedral hidden subgroup problem, which would break many lattice-based cryptosystems, is a well-studied open problem. It has been proven that applying Grover's algorithm to break a symmetric algorithm by brute force requires time equal to roughly 2n, 2 invocations of the underlying cryptographic algorithm, compared with roughly 2n in the classical case, meaning that symmetric key lengths are effectively halved. AES 256 would have the same security against an attack using Grover's algorithm that AES 128 has against classical brute force search. Quantum cryptography could potentially fulfill some of the functions of public key cryptography. Besides factorization and discrete logarithms, quantum algorithms offering a more than polynomial speedup over the best-known classical algorithm have been found for several problems, including the simulation of quantum physical processes from chemistry and solid-state physics, the approximation of Jones polynomials, and solving Paul's equation. No mathematical proof has been found that shows that an equally fast classical algorithm cannot be discovered, although this is considered unlikely. For some problems, quantum computers offer a polynomial speedup. The most well-known example of this is quantum database search, which can be solved by Grover's algorithm using quadratically fewer queries to the database than are required by classical algorithms. In this case, the advantage is provable. Several other examples of provable quantum speedups for query problems have subsequently been discovered, such as for finding collisions in 2-to-1 functions and evaluating NAND trees. Consider a problem that has these four properties. The only way to solve it is to guess answers repeatedly and check them. The number of possible answers to check is the same as the number of inputs. Every possible answer takes the same amount of time to check, and there are no clues about which answers might be better. Generating possibilities randomly is just as good as checking them in some special order. An example of this is a password cracker that attempts to guess the password for an encrypted file. It can be used to attack symmetric ciphers such as triple-DES and AES by attempting to guess the secret key. Grover's algorithm can also be used to obtain a quadratic speedup over a brute force search for a class of problems known as NP-complete. Since chemistry and nanotechnology rely on understanding quantum systems, and such systems are impossible to simulate in an efficient manner classically. Many believe quantum simulation will be one of the most important applications of quantum computing. Quantum simulation could also be used to simulate the behavior of atoms and particles at unusual conditions such as the reactions inside a collider. There are a number of technical challenges in building a large-scale quantum computer, and thus far quantum computers have yet to solve a problem faster than a classical computer. David DiVincenzo, of IBM, listed the following requirements for a practical quantum computer. Scalable physically to increase the number of qubits. Qubits that can be initialized to arbitrary values. Quantum gates that are faster than decoherence time. Universal gate set. Qubits that can be read easily. Quantum decoherence. One of the greatest challenges is controlling or removing quantum decoherence. This usually means isolating the system from its environment as interactions with the external world cause the system to cohere. However, other sources of coherence also exist. Examples include the quantum gates, and the lattice vibrations and background thermonuclear spin of the physical system used to implement the qubits. Coherence is irreversible, as it is non-unitary, and is usually something that should be highly controlled, if not avoided. Coherence times for candidate systems, in particular the transverse relaxation time T2, typically range between nanoseconds and seconds at low temperature. Currently, some quantum computers require their qubits to be cooled to 20 millikelvin in order to prevent significant coherence. These issues are more difficult for optical approaches as the time scales are orders of magnitude shorter, and an often cited approach to overcoming them is optical pulse shaping. Error rates are typically proportional to the ratio of operating time to coherence time. Hence, any operation must be completed much more quickly than the coherence time. If the error rate is small enough, it is thought to be possible to use quantum error correction, which corrects errors due to coherence, thereby allowing the total calculation time to be longer than the coherence time. An often cited figure for required error rate in each gate is 10⁻⁴. This implies that each gate must be able to perform its task in 1/10,000th of the coherence time of the system. Meeting this scalability condition is possible for a wide range of systems. However, the use of error correction brings with it the cost of a greatly increased number of required bits. The number required to factor integers using Shor's algorithm is still polynomial, and thought to be between L and L2, where L is the number of bits in the number to be factored. Error correction algorithms would inflate this figure by an additional factor of L. For a 1000-bit number, this implies a need for about 104 bits without error correction. With error correction, the figure would rise to about 107 bits. Note that computation time is about L2, or about 107 steps, and on 1 MHz, about 10 seconds. A very different approach to the stability decoherence problem is to create a topological quantum computer with any once quasi-particles used as threads and relying on braid theory to form stable logic gates.